So AC integrator is a modification to the true integrator that we discussed earlier. And as we discussed that the true integrator circuits, if you have a small biasing current at the input of the integrator of the op amp, or any stray noise, DC noise, then since the function of integrator is to accumulate, to add, um, that small noise or biasing current or voltage can keep on accumulating and appears at the output until it hits the saturation level. So even though you don't have any input you don't have any input signal, but any stray noise or the DC voltage or DC biasing current, which usually have very small value, may push the true integrator into saturation at the output. To alleviate this problem, we modify the true integrator circuit and we create an AC integrator. As you can see the circuit in figure 5.5, you have the true integrator, and we're going to modify this true integrator into AC integrator. Before we do that, we're going to go ahead and write down the transfer function, that is the output voltage over input voltage for the true integrator. And then we are going to write down the transfer function of the AC integrator and compare with each other to show that at certain frequencies, true integrator works, AC integrator works as a true integrator, over which the noise is not going to impact the output. And at other frequencies, the operating frequencies, that is, the AC integrator works as at operating frequencies, it works as a true integrator, and at other frequencies, which are low frequency or at DC, it works as a simple inverting amplifier. So we're gonna convert this circuit into phasor domain. So you're gonna have V input j omega, you're gonna have V output j omega, and then you are going to have the reactance of the capacitor, which is simply 1 over j omega c. And you can see that in the second figure. And when you write down the transfer function, that is gain, transfer function and gain is the same thing here. V output j omega over V input j omega, the ratio between the output and the input, which is h of j omega. And we are going to apply basically KCL at the inverting input where you have virtual ground. So the current that is going towards the virtual ground, let's call this current I input, and the current that is passing through the capacitor, we call this current IC. So current I input is simply V input divided by R when you apply KCL here. And of course, you have the current IC, which is going to be 0 minus V output over XC. So if we apply KCL at virtual ground, and let me erase this. I'm just going to write down here. So you're going to have KCL at virtual ground. You're going to have I1 is equal to IC, which is V input over R. V input j omega, remember, is a function of complex frequency omega, is equal to negative V output over XC, which will give us V output over V input. And again, this is a function of j omega, but we don't really have to show it over and over again. V output over V input is equal to negative XC over R. And XC, of course, is negative 1 over j omega c, so 1 omega j omega c r, which you can see is here, which is your transfer function, output over input. So for the true integrator, this is your transfer function in the complex frequency domain. The AC integrator, and since it's a complex quantity, of course, then the magnitude, it has a magnitude and the phase. And we know that the magnitude of this is simply going to be 1 over omega CR. And what is going to be the phase? The phase of this is simply going to be, we're going to take J in the numerator. It is going to become negative J. So negative J times negative is going to become positive. So we can write this as J over omega CR. Therefore, the phase of this is simply 90 degrees, which is J1. So the phase of the transfer function is 90 degrees and the magnitude is 1 over omega CR. Magnitude is represented by m of omega as a function of the angular frequency, 1 over omega RC. And as I said, phase of h of j omega is simply 90 degrees. That is a constant angle at all frequencies. Now, at DC, if you look at this, the gain is going to be infinity for this circuit because DC has a frequency 0. So when you put 0 over here, or when it tends to 0, the gain will keep on increasing, and at 0, it is going to hit infinity when you take the limit. And that is the issue that we discussed, because the gain is just so large for the circuit that it will make the output saturated for any input DC value, as we discussed earlier, for any DC biasing input. Any small DC biasing input, the output is just going to hit infinity. Okay, so how do we change that into AC integrator? As you can see, very easy. We just use a resistance in parallel to the capacitor in the feedback loop. As simple as that. And the reason, let's discuss the reason why, what is going to happen. So remember, at DC, the capacitor acts as an open circuit because the reactance of the capacitor is 1 over, the magnitude of reactance is 1 over omega C. So when omega is 0, then this is going to be extremely large, infinity, which means that the reactance of this capacitor is going to be infinity, means open circuit. So at DC, this is going to act exactly as your inverting amplifier with the gain RF over R input. So any DC biasing voltage that is at the input, very small value, it is not going to act as integrator. It is going to act as an inverting amplifier, and the output is going to be according to the gain of the inverting amplifier to produce the output corresponding to any DC quantity at the input, whether it's a small noise voltage, a small DC bias, or actual DC voltage. When the frequency keeps on increasing, then the reactance of the capacitor will keep on decreasing. And at one time, of course, the reactance capacitor is going to become quite small, such that most of the current is going to flow through the capacitor, and current is not going to flow, or very small current is going to flow through the feedback resistor. So at that time, or at those frequencies, the circuit will start working as a true integrator because RF effect is going to be nullified by the reactance of the capacitor. And we're going to discuss what frequencies they are going to be. So once again, when we convert this circuit into phasor domain, as you can see, we input j omega, we output j omega, and reactance of the capacitor 1 over j omega c. Now, these two are in parallel with each other. So we can write down the parallel equivalent, RF parallel to XC, which is 1 divided by 1 over RF plus 1 over XC, which will give us 1 over RF, and XC, remember, is 1 over j omega c. So 1 over j omega c will simply be j omega c, which will give you RF over 1 plus j omega RFC. So that is going to be the parallel combination of these two components, RF over 1 omega over 1 plus j omega RFC, which you can see in equation 5.5. So the transfer function or the gain, again, we can write down the transfer function of this circuit, replacing XC and RF by Z, then is simply going to be an inverting amplifier. So the transfer function or the gain of the circuit, H of j omega, which will be the output over input, we know that it's going to be negative. Feedback impedance in this case will be Z over input resistance, which will be R. And then we can simplify that by putting Z is equal to RF over 1 plus j omega RFC, which you can see over here. We replace ZF over this. And then further simplification is going to produce this equation right here. RF over R input, negative RF over R input divided by 1 plus j omega RFC. RFC is the time constant of this parallel RC circuit, RF and C. So RFC is the time constant of that. As you can see, tau F. And then we can also write this down as negative, let me write down here, negative RF over RI over 1 plus j omega divided by 1 over RFC. It's the same equation. Instead of writing omega RFC, I write down omega over 1 over RFC, and this is going to be the breaking frequency or cutoff frequency. Breaking or cutoff frequency. Because the expression, if you look at the expression, it is like a low-pass filter expression. So at the breaking or cutoff frequency, what's going to happen? The gain of the amplifier is going to be 70.7% down from its DC gain. And remember, the DC gain is RF over R input. So that is going to be at the breaking frequency. And that's what you see here in this expression, negative RF over R input, 1 plus j omega over omega B. So if omega is DC, that is 0, then this term is going to be 0, j omega over omega B, and the transfer function will simply be negative RF over R input. That is at DC frequencies, it is going to act, as we discussed earlier, as an inverting amplifier with the gain negative RF over R input. And if omega becomes larger than omega B, quite larger than omega B, then we can ignore this 1. We can ignore this 1 if omega is quite larger than omega B right here, or F is quite larger than FB. And once you ignore 1, this RF and RF will be cancelled out, and you are going to get negative 1 over j omega R input C. So your transfer function is going to become, after cancelling out this RF and ignoring 1 over j omega R input C. And guess what? J omega R input C is the transfer function of your true integrator, which means that at frequencies quite larger than the break or cutoff frequencies, this circuit is going to be operating exactly or approximately, let's say, or very close to, as a true integrator circuit. So this way, we can take care of any DC biasing input, stray input, because at DC frequencies or low frequencies, the circuit is not going to be operating as AC integrator. It's not going to accumulate that input and project it at the output and eventually saturate. But this is going to be operating as an inverting amplifier with the gain RF over R input at DC or low frequencies. However, when the frequency exceeds, if your operating frequency is quite larger than omega B, then the circuit is going to operate exactly as the true integrator with it's going to basically shape the waveform of the input to the output, or it's going to add up all the area under curve of the input waveform and project the output based on that. So that is how it's going to work. Now, when you're calculating the output, it is very easy to divide the input into 2 signals. One signal is if you have a DC component of the signal, and one component is the AC component of the signal. The DC component of the signal, for the DC component of the signal, the output can be calculated by simply assuming the AC integrator to be an inverting amplifier. And for the AC component of the signal, the output is calculated using the concepts of true integrator. However, make sure that the frequency, the AC frequency, must be quite larger than your cutoff frequency in order for the circuit to work as a true integrator circuit. So for example, if you have a waveform, let's say a sinusoidal waveform or any waveform like this, and this waveform is centered at, let's say, 3 volt, and the peak value is 5. That means you're going from 5 to, let's say, 1 volt. So 3 plus 2, 5, and then so the peak value of the waveform is 2 volt. So it's going between 2 volt and negative 2 volt, but it has a DC offset of 3 volt. So you can divide this into two signals. You can have a signal, DC signal 3 volt, which is DC, and then you can have an AC signal, which is a sinusoid, which is 2 volt peak sinusoidal waveform, 2 and negative 2. So when you're calculating the output of the AC integrator, you can calculate the output corresponding to 3 volt DC. Let's say that the gain RF over input is 2. Then the DC component at the output is going to be 2 times 3, 6, and negative sign, negative 6. So it's going to be negative 6. And the AC component, remember AC component is about the time domain, the time axis, which is basically zero DC component is about the x-axis or time axis. So for the AC component, you're just going to use this to calculate the output of the AC integrator. Integrate the sinusoidal waveform. If it's sinusoid, it's going to give you cosine signal, of course, and then the gain of the amplifier is 1 over R input C that you're going to multiply by that. So the output is going to be a sinusoidal signal, which will be centered at negative 6 volt for this circuit if our DC component is 3 volt and gain is RF over input is 2. So this is how we can easily calculate the output of AC integrator if we know the DC component at the input as well as the shape of the input. Let's look at this example, example 5.2. In this case, we have an AC integrator. So let's say you have input, negative, positive. So this is your circuit, V out, V in, R input, RF, and C. And C is given as 0.1 microfarad, R input is given as 5K, 0.1 micro, and then RF is given as 10K. And we are giving this waveform at the input. Now this waveform, observe the time period is 1 millisecond. This is the time period. And this waveform is a square wave going from 2 volt to 4 volt. Now I can break this waveform down into DC component, that is the middle value, which is 3 volt, and a square wave going between 1 volt and negative 1 volt. So this component can be, this input can be written down as a DC component of 3 volt plus an AC component of a square wave between negative 1 and positive 1. So this is the AC component. So when you add these two, of course, you're going to get the square wave offset by 3 volt. So when you're calculating the output of the signal for the DC component, of course, you're going to use the DC value, and for the AC component, you're going to use the AC value. Now on the right-hand side, you can see some calculation to show you that for the AC input, it will work as a true integrator because we are calculating the break frequency and comparing that break frequency by the frequency of the signal, which is 1 kilohertz. Since the time period is 1 millisecond, the frequency is going to be 1 kilohertz for this square wave. And then we calculate the break frequency, which is 1 over RFC, came out to be 1 kiloradian per second. And then when you convert that into cyclic frequency in hertz, then omega b over 2 pi is going to give you 159 hertz. 159 hertz is quite smaller than 1 kilohertz. Therefore, the AC component, for the AC component, the circuit is going to work perfectly good as a true integrator circuit. And of course, for DC component, capacitor is going to be open circuit and it's going to work as an inverting amplifier. So let's calculate the output of this. The first, as we already discussed, V out DC is equal to negative RF over RI, V input DC, which will be RF is 10, RI is 5, so 2, negative 2 times V input DC is 3, so negative 6. So the offset at the output is negative 6 volt. As far as input is concerned, so this is my AC signal centered at 0. And let's go ahead and calculate either the positive area or the negative area to find the peak-to-peak value. So if you calculate this area, the height of this is 1, and the width is half of the cycle, which is 0.5 milli. The 1 times 0.5 milli is 0.5 milli. So V out AC peak to peak is equal to negative 1 over RC, R input C, negative 1 over R input C, and integral of that. Negative 1 over R input C. R input is 5K and C is 0.1 micro. Kilo and micro are going to be milli, and 5 times 0.1 is negative 0.5. So 0.5 milli times the area under curve, positive or negative, whatever. So that is, what did we say? 0.5 exponent negative 3 times 1, so 0.5 exponent negative 3. So these two cancelled out, and this is going to give us, and we can just take the magnitude because we are doing peak to peak. So drop this negative 1. So the peak to peak value is 1 volt peak. So the output of this circuit is going to be time scale V out and time scale. Let's say this 0.5, this is 1 millisecond, 1.5 millisecond. Assume time scale is in millisecond. So 0.5, 1 millisecond, 1.5. Now I have the AC component at negative 6. Let's say this is negative 6. I mean DC component. So this is negative 6 volt. And then I have, let me draw a line. And my AC component is riding on that DC component. So my output is going to be, now remember, because of this negative sign, if my input is high, half of the cycle, the first cycle, the slope of the output, negative 1 over RC, the slope of the output is going to be going down. So it's going to, and the peak to peak value is 1 volt peak to peak. That means it's going to go from negative 5.5 to negative 6.5. Right? Because the peak to peak output is 1 volt peak to peak. So it's going to go from here to here, and then from here to here, and then here. So it will keep oscillating, of course, as the square wave is going to convert into triangular waveform or ramp signal. And then this will keep on going. If the first one is going to be the negative value of the square waveform, then it's going to start increasing. So if you want to start from this point, at 0.5 millisecond, then of course it's going to increase first because you have a negative value. So your slope is going to be positive because of this negative sign that you had. So to understand the concept, of course, you're just calculating peak to peak value over here, but the negative sign basically is going to change the slope of the output with respect to the input. So this is going to be the output waveform of this AC integrator for the specs that are given and the signal that is given to the inverting the AC integrator. All right, the next topic is the low frequency differentiator. Now, once again, remember the true differentiator, the issue was that if any small noise that arrives at the input for a very brief amount of time, then since it's a differentiator, it takes a rate of change, even though the noise may be very small, but the duration for which it is going to last may even be smaller. So when you take the dV over dt, the rate of change can be very large, and that can send spikes at the output, impulses at the output whenever that happens. And then, of course, it's not going to work in the real world situation, especially if you have noisy environment. So to take care of that, we create low frequency differentiator. It's a differentiator that is going to work as a differentiator at low frequencies, and at high frequencies, it is going to work as inverting amplifier up to certain value, of course. And after that, we're going to discuss after that, it's just going to, the gain is just going to be start going down. So this is your AC low frequency integrator. You added a resistor in series with the input capacitor. Once again, we are going to go ahead and convert this model into phasor form. So we input j omega and x of c. This is x of c 1 over j omega c and RF. Don't worry about this additional capacitor because for the wideband operational amplifier that it may have another capacitor in parallel with RF. So now we can calculate the series impedance of R input in C, which will be R input plus XC, which will be equal to R input plus 1 over j omega C, or 1 plus j omega R input C over j omega C. That's your input. That's your impedance of the input resistance and capacitor. And then, of course, your transfer function, which is the output over input, it will act as an inverting amplifier with the inverting impedance to be Z, or you want to call it Z input, whatever. And the feedback is RF, so it's simply going to be RF over ZI, which is equal to negative RF over 1 plus j omega R input C over j omega C. This j omega c is going to go in the denominator. In the numerator, it's going to become j omega RFC over 1 plus j omega R input C. And again, we can write this down as negative j omega RFC over 1 plus j omega divided by 1 over R input C. And then this can be considered as your break frequency, omega. And the derivation is given right over here. So once again, the magnitude response, we can see the magnitude response is going to be the magnitude of the numerator, which is omega RFC, and the magnitude of the denominator, which is going to be square root of real part square, 1 square, plus imaginary part square, omega R input C square, which is right here. Tau input is the time constant of the input series R input and C circuit. And again, I showed you the omega B, the break frequency, which is 1 over R input C, which is right over here. Okay, so break frequency. If omega is much larger than the break frequency, then what is going to happen? We can ignore this one. Once again, if omega is much larger than the break frequency, we can ignore this one or this one, whatever you see. That means j omega will be cancelled out by j omega. C will be cancelled out. And you're going to be left with negative RF over R input, which is your inverting amplifier. Which means that for all the frequencies larger than the break frequency, the circuit is going to be working as an inverting amplifier. And below that, if omega is less than omega b, then what is going to happen? Again, let's go back to this. We can just right here. We can just discuss this. If omega is much smaller than omega b, then we can assume that omega over omega b is very small as compared to 1. We can ignore it, and our transfer function will simply be negative j omega RFC, which is the transfer function of your true integrator, true differentiator, the magnitude of which, of course, is omega RFC. So it is going to work as a true differentiator circuit at low frequencies, and at high frequencies, it is going to work higher than omega b. It is going to work as inverting amplifier. But there's another thing. Remember, in the last chapter, in chapter number 4, we discussed the effect if your input signal is sinusoidal, then the effect of the closed loop bandwidth and the slew rate. Now, it is working as a differentiator, let's say, until omega b. And then after omega b or fb, it is going to start working as an inverting amplifier with a gain RF over R input, let's say. And this is, let's say this is omega b or fb. And this is the differentiator, true differentiator. But remember, you also have the closed loop bandwidth of any circuit. And we know at closed loop bandwidth of the circuit, let's discuss basically your inverting amplifier. At closed loop bandwidth, the gain is going to be down by 70.7% of the DC gain, right? Which is basically RF over R input. So it is not going to work as inverting amplifier for all frequencies above FB. It is going to work pretty much until BCL, and after BCL is going to start going down. The gain is going to start going down. So this is pretty much how the low frequency differentiator is going to work. It is going to work up to FB. It is going to work as low frequency the true differentiator. Below FB, frequencies larger than FB, much larger, it is going to work as an inverting amplifier. And then after BCL, of course, the gain is going to start dropping, as we discussed in chapter number 4. And that is explained over here. So as long as omega is quite smaller than omega b, the circuit is going to work as a true differentiator circuit, and the output can be calculated by the equation of the true differentiator that we discussed earlier, that is negative RFC, rate of change of the input voltage. Now, one thing is input, as we discussed for the integrator. Input signal may or may not have DC offset. And we saw that for the integrator circuit, if you do have a DC offset, then you will have a DC offset at the output as well. Because the AC integrator circuit, it is working as inverting amplifier up to the cutoff frequency, and it is working as an integrator, true integrator, after the cutoff frequency. So at DC, basically, it works as an inverting amplifier. For the differentiator circuit, if you have a DC value at the input, what is going to happen? Any DC voltage, when you take the derivative, it's going to become 0 at the output. So at 0 frequency, that is a DC, irrespective if you have an offset at the input or if you don't have offset, the output corresponding to that is going to be 0. That is, the output DC is going to be 0, which means the output will always, the waveform will always be centered about your x-axis, time axis. And since the differentiator circuit basically it gives you slope, then you can figure out what is the, of course, we know the shape. For example, we discussed different shapes earlier, that if your input is a square waveform, impulses, triangular waveform, differentiator is going to give a square, sinusoidal is sinusoid, and so on and so forth. So we already know the shape based upon the input to a differentiator circuit. But what will be the peak-to-peak value? How are you going to calculate that? To calculate the peak-to-peak value of the output, of course, the gain is negative RFC or RFC. The gain, as we know that it is RFC, negative sign, of course, represent that the slope is going to be opposite of the input. And the derivative represents slope. Remember, slope of the input signal. So to calculate the peak-to-peak value of that slope, we calculate the positive slope and add the negative slope. And that shows you what is the peak-to-peak value of the slope times, of course, RFC. What is the peak-to-peak value at the output? That's an easy way to do it if your input signal has consistent slopes. So let's look at the success. A low frequency differentiator has a triangular waveform applied to an input as shown in the figure. Calculate and determine its output. So although this output, the DC value is 0, but even if this DC value is not 0, and if this triangular waveform is riding on 3 volt or 5 volt or negative 5 volt, doesn't matter. That DC component, when it passes through this differentiator circuit, it is going to become 0 at the output. So we don't have to worry about the DC component at the output. We know the AC component shape is going to be what? Since input is a triangular waveform, a ramp signal, an AT signal, when you take the differentiation of AT, then you're going to get A. So it's a constant value. It's going to be a square wave. It's a constant square wave at the output. And what will be the peak-to-peak value of that? So we have, again, 1 millisecond is the wave. Time period is 1 millisecond right here. And you can also calculate the break frequency just to make sure that it is operating below the break frequency such that it is acting as a true differentiator circuit. So the break frequency, omega B, is 1 over, let's see, where did I do it? 1 over R input C. 1 over R input C, which is R input is 100 ohm, C is 0.1 micro. So 1 divided by 100 times 0.1 is 10, so 10 micro. Which will be 0.1 exponent 6 or 100 kilohertz, 100 kiloradian per second, which can be converted into 100 over 2 pi k, and that is going to be, let's see, we do it quickly. 100 exponent 3 divided by 2 times 5 is 15.9 kilohertz. 15.9 kilohertz. 15.9 kilohertz, and the input frequency is again 1 kilohertz because the time period is 1 millisecond. Therefore, the input frequency is quite smaller than the cutoff frequency. Hence, this circuit is going to work safely for the input signal. It's going to work safely as a true differentiator circuit. So the output value, if we calculate that, we know the output waveform is going to be a square wave, and the output value is going to be V out peak to peak is going to be 1 over RF or RF times C. Sorry, it's just a magnitude. Let's calculate magnitude. RF times C and the positive slope plus magnitude of the negative slope. So RF times C 10 times 0.1. So 1 and micro and kilo is going to be milli. So 1 milli, 1 exponent -3. And the positive slope is going to be, what will be the positive slope? Let's see, from -2.5 to 2.5 divided by 0.5 millisecond. So 5 divided by 0.5 milli. And the same thing is the negative slope, area, just the magnitude, 5 divided by 0.5 exponent -3. So we're going to get 1 exponent -3 and 2 times 5, 10 over 0.5 exponent -3. So exponent 3 and exponent 3 is going to be cancelled out. And that's going to be 20 volt peak to peak. So the output signal is going to be a square wave with peak value to be 10 and -10 minimum value. So we output and time scale. Since the slope is going down first, you're going to have positive first and then negative, and then positive and then negative, and so on and so forth. So you're going to have 10 volt and you're going to have -10 volt, 0.5, 1, 1.5. Time is in millisecond. And this is going to be the output of this AC or low frequency differentiator circuit.